sparsity or Lasso. So let's get right into it. So just to recap, as always, we have this supervised learning pipeline where we have a training set. We have model class or a collection of model classes. We'll talk about that more carefully this lecture. We choose a loss function. We went through a bunch of different loss functions last lecture. Today, I think we'll just stick with squared loss again, just to keep it simple while we talk about other aspects of this problem. And then we do some cross validation or model selection. We solve this learning problem on the training set using stochastic gradient descent. And so that's the entire pipeline that we've talked about so far. Okay? So today we're going to focus on different types of model classes and what this and how to use, subsequently use the validation set or cross validation to do model selection. Okay? And so here's one option, right? Last lecture we learned about SVMs, artificial neural nets, logistic regression, least squares regression, something we've been talking about for a long time. So perhaps, the choice of the loss function, right, could be something that we choose using cross validation. We see which loss function actually minimizes the 0-1 loss on the validation set the best, and then we simply choose the loss function that achieves the lowest 0-1 loss, because as you may remember, all of these loss functions are surrogates to 0-1 loss because minimizing 0-1 loss directly is intractable because it is flat or discontinuous everywhere. So that's one option. Option two, which will be the focus of this lecture, is regularization. Okay, so first some notation. So we're going to use the concept of norms a lot this lecture. So there's the L0 norm, which by the way is not actually a norm. It doesn't satisfy certain properties of norms in, for example, metric spaces. And the L0 norm, again, just informally, not a norm, counts the number of non-zero entries, right? So it's typically denoted as follows, and it simply counts the number of times an entry in this vector, our model vector, is non-zero. Okay? The L1 norm is the sum of the absolute values of the entries in our model vector, or any vector, but typically we use it to measure, we measure these norms on our model vector. The L2 norm, or which is usually what we refer to as L2 norm, is actually the squared L2 norm. The L2 norm is the square root of the sum of squares of the entries in the weight vector. This is the default norm in most cases. In machine learning, we often use the square of the L2 norm, right? This guy, which is could be equivalent written as the vector, the dot product of the vector with itself, right? And we saw this being used when we looked at SVMs in the previous lecture, and today we'll be talking more about it. And then there are other concepts like the L infinity norm, with an infinity in the norm subscript, which is simply the, we take the limit of the polynomial root power raised of each sum of each entry raised to that same power as that power goes to infinity. Right? So when p equals 2, you get the 2 norm. When p equals 1, you get the 1 norm. And as p goes to infinity, you get the L infinity norm, which, in the limit becomes simply the size or the absolute value of the maximum entry of W. So these are the concepts that we'll be using to measure model complexity, which is going to be used as a way of doing what's called regularization. And that'll be the focus of this lecture. Okay. So today we'll be typically talking about squared loss, just for brevity, we'll simply call it regression. Right? When people say regression without any extra adjectives or modifiers prepending to regression, you should just assume that they're talking about least squares or squared loss regression. For example, if they're talking about some other form of regression, they would say logistic regression, which means minimizing log loss and not squared loss. But if they just say regression, typically people just mean minimizing squared loss. Just a bit of notation shorthand. And again, in the lecture, we'll just be focusing on squared loss in lecture today. Although the concepts that we'll be talking about are of course compatible with most loss functions, such as hinge loss. Okay, so ridge regression. Ridge regression is given by the following optimization problem. It is essentially just minimizing the regression error, which is squared error, right? The model class, right? A linear model class is a bias term, right? The difference between the target label of this training example and the prediction of our model, computed by as measured with the mismatch as measured by squared loss, plus this what's called a ridge term. This is also known as L2 regularized regression, right? Because this is the L2 norm, right? So now we want to find the W and B that minimizes the square loss on the training examples and the L2 norm, or squared L2 norm, of our model vector with this lambda term, which is a non-negative term, controlling this trade-off, right? And you can think of this, and we'll talk about the intuition about why this is the case, but you can think of this as this optimization problem or learning problem as trading off between a measure of model complexity versus fitting the training set, right? And so you can think of the L2 norm, or the squared L2 norm, of the model vector as a measure of the complexity of the model. Yes?
This might be an FB, but I just want to make sure notation doesn't change. Is it plus B or minus B?
So I believe we do y minus f of x, and f of x is w transpose x minus b.
Minus, okay.
Yeah. And so as we'll see later in this course, each choice of lambda, you can think of it as corresponding to a different choice of model class. And you'll see the mathematical connection later on in this lecture. Okay, so just a very simple example, right? Suppose we have two features in our feature vector, and they're both indicator features. So one, if the person, so each entry x is a row here, right? And x corresponds to a person with two features, an indicator vector, a variable that's one if and only if age is greater than 10 and 0 otherwise, and one if the gender is male and 0 otherwise. And the target label that we're trying to predict is whether or not the height of this person is greater than 55 inches or less than or equal to 55 inches, encoded as 1 or 0, respectively. You can, of course, also encode this as 1, plus 1 and minus 1. We'll just do 1 and 0 just for the simplicity of this example. And then we collect the training data. This could be a representative sample of the training data. And then we solve this learning problem, right? We want to learn a WB that predicts Y given this X. Right? And suppose the top half is training and the bottom half is test, right? Then, what I'm giving you here is the solution of W and B of this optimization problem as lambda increases. So the first one is when lambda is the smallest, the second one is when lambda is very big. And so let's just take a look at what's going on here, right? So when lambda is very small, we get a W and B that, as you look at the error, it actually fits the data pretty well. And then as lambda increases, right, then this term matters more, right? The norm of W matters more when you minimize this optimization problem, right? So you want to, if lambda is 10 times bigger than before, then you care about this 10 times as much as you care than before relative to how much you care about it relative to this term, right? And so as lambda gets very large, then you actually want this to be really, really, really small. And then your W becomes really, really, really small, right? So for very, very large lambda, the solution to this optimization problem has W being very, very, very small. Now, in this particular formulation of the optimization problem, we're not regularizing the bias term, right, the B, right? And so if you actually look at the training set, right, 2/3 of the 6 instances, 4 out of the 6 training instances, has y equals 1, and 1/3, 2 out of 6, has y equals 0. And so if w is basically modeling nothing, right? It's just the 0 vector essentially when lambda is really large, then in order to minimize the square loss, right? If this term is basically 0, right? What is the b that minimizes squared loss, right? It is the average y, or the negative of the average y depending on the sign of b, right? Which is exactly 2/3, right? Yes?
Is there any reason you might want to regularize your bias term?
Sometimes it's for mathematical convenience, right? You know, you just add you add it as a you add a constant feature to your x, in which case w is just assumed by b is subsumed in the w. Often I do this all the time, just for convenience, right? And it typically doesn't matter that much because the feature is always on, right? And so even if you regularize, it won't change it that much. So the bias term is pretty impervious to regularization. In general, I think, you know, no, you don't. In general, you don't want to, but regularization typically has a minimal effect on the bias term because the feature is always on, right? Yes?
Unless that also mentioned like normalize the input, each like dimension the input to be like 0 and be 1. Would that also send?
It would change. It wouldn't change this. It wouldn't change this outlook. It might change what values of lambda achieve this trend. It wouldn't change the trend. Does that make sense?
Would it affect the bias?
I'm sorry, what?
Would it affect the bias?
Well, you know, if I turn up regularization so large that I pay a huge penalty whenever w is non-zero, like down here, then the bias is simply going to be the average or the negative of the average label, right? So it wouldn't change that in this case, even if you normalize the x, right? So when the regularization is really, really, really high, let's say we could set lambda to be infinity, right? Then w would have to be exactly 0, because whenever w is not 0, this term is infinity, right? So, you know, therefore this term is 0, right? And therefore all we're learning is the population average, right? B measures the population average, right? What on average, 2/3 of these people are greater than 55 inches, and B is basically exactly corresponding to that, right? And that is, in some sense, the simplest model you can learn, right? I'm just going to ignore any of the features and just learn to predict the population average, right? That is the simplest model that you could possibly learn that captures any information about this training data. Right. Just as a thought experiment. Yes?
When you split up your model into training data and test data like this, once you're done with estimating the out-of-sample error, you would still train on all the examples, right, to get your final model.
Right. So one of the most common things to do is to, and we'll talk about this later on in the course with more sort of plots and figures and examples, but if you set lambda to be really small, then you can overfit, you can learn a W that overfits to your training set. Right? And whenever loss you get on the training set, you get much higher loss on the test set. So then you set a lambda that regularizes a little bit enough so that you don't overfit to the validation set, I guess I should say. And then you find the lambda that minimizes the validation error, and then what people often do then is fix that lambda, right? And then retrain once on the whole training set, and then just commit to that. Yeah. Okay. That's often what people do. Okay, and so here's a plot of as you increase lambda, and note the lambda here is on a log scale, not a linear scale. So every set of ticks is a factor of 10 increase in lambda. And so here is training loss in red and test loss in blue, right? And so, as the lambda is really small, you fit the data as well as you possibly can, effectively, right? Because basically, lambda is really small. This term is negligible, right? You'll pick whatever W you need to fit the training data as well as possible. Well, lambda is really big. Oops. Sorry. Well, lambda is really big. You pay a penalty when you have a large W. So you want to pick a really, really small W. And given a really, really small W, you try to fit the data as well as possible. Of course, you can't. And so you pay a larger training loss. So the training loss will always increase as you increase lambda, because you're compromising or you're handicapping the ability of your learning algorithm to actually fit the data when you increase lambda, right? But, right, we talked about overfitting, right, in the first lecture, and we've been talking about it ever since. And so, if you don't use lambda, you may be overfitting to your training data, and you could do better on your validation, or I guess we'll test here, but you could also do this in your validation set if you increase lambda. And as you can see, indeed, for this, at least for this toy example, right, the test loss actually is lowest for some intermediate value of lambda, right? And then as you increase lambda even more, then you're just learning the population average, which has a higher test loss than learning something in between. Yes.
Does this indicate that by making lambda larger, that there's some overfitting going or in the model when we have lambda that's negligibly small?
That's right. This is it. I mean, first of all, here we are also overfitting. We're just overfitting less.
Okay.
Yeah. Right. And of course, these curves are going to look different as you get training data of different sizes, different number of features, and all that stuff. This is just qualitative. Just take this qualitatively. Right. Yes.
But intuitively, why would increasing lambda would, if we look at the sweet spot, why would adding a lambda decrease the degree of overfitting, I guess?
So why would increasing lambda decrease the test loss? Was that your question?
And overfitting is defined like will prevent overfitting, I guess, instead of test loss. Because overfitting is a general concept that's describing the test loss, test error is much larger than the training error.
That's right. So regularization, at least in this example, and in general, it tends to be true. As you increase regularization, you can control for some amount of overfit.
But why is that?
Why is that?
Yeah.
Well, okay. In the simplest case, so let's just look at this example here, right? Which let's just look at this simple example, which is a subset of the training set, right? Just this very simple example. If I make lambda huge, right, such that let's say we make lambda infinity, right? Then the only thing that we can learn is the b, right? That's the only thing we can learn because w is forced to be 0, right? Because whenever w is not 0, we pay an infinite penalty because lambda is infinity, or effectively infinity, right? Like I could just, like in practice, you just set lambda, if you want to do that, you set lambda to like 100 trillion or whatever, and that'll effectively make it infinity for numerical purposes. And so b then would be 2/3, or I guess negative 2/3, it's a minus b, because that's the population average, right? Minimizing square loss, if this part is 0, is just simply setting b to be the average, right? Okay, it turns out, at least in this example, 2/3 of the training set has y equals 1, and 1/3 has y equals 0. On the test set, indeed, 2/3 of the examples have y equals 1, and 1/3 has y equals 0. So I would get an error of, average error of okay, can't do math in real time anymore. But you get some average error on the training set, in terms of square loss. And indeed, you would get the exact same error on the test set. You would get 0 overfitting, right? Because the average is exactly the same, because exactly 2/3 of the test set has y equals 1, and exactly 2/3 of the training set is y equals 1. So if you jack up your regularization term to infinity, you w equals 0, you just learn b, which is the population average, you overfit by 0. You don't overfit at all. Right? Because you've learned the simplest possible model, which is simply the population average. And if you, which has one parameter, b, that's allowed to be free. And that parameter actually does not overfit in this very simple example.
And just to clarify,
Yeah.
where would you assume that the average would be the same for training data and test data? That is,
Oh, I mean, in general, it's not, right? But they're going to be close, right? It's just because it's just one number, right? Yes.
If we're taking lambda that minimize the error we see in the test set, might we be worried about some sort of overfit to the test set?
That's right. So when you do cross-validation, you're picking the lambda that minimizes error on the validation set, right? And yes, you are going to be overfitting a little bit to the validation set. That is a risk, yes. But in some sense, that's the best you can do. Okay, so this is the updated pipeline, right? We have a training data, we choose a model class, we choose a loss function, and we have this regularized learning problem where we minimize the loss function. And again, in this lecture, we're just going to focus on squared loss, just to keep that part simple. Plus a regularization term, right, that controls for complexity. We're going to do cross-validation, and we're going to pick the lambda that minimizes the error on the validation set, right? And that's what model selection is. That is an instance of model selection, right? Because every lambda, and we'll see this more clearly as the lecture goes on, corresponds to a different model class. And so, the calculus competition is on the horizon. And so this is basically what most of it is going to be about. Okay. So here I'm just giving you the score. I'm just printing out the score that the learned model would give on this example, right? And so I train a model to minimize. I train a model under some lambda, and then I ask that model to make a prediction on every example, right? And this is the prediction that the model makes on every example for 5 models that are trained using different values of lambda, right? So every column is the predictions of the model on different values of lambda, and every row, it corresponds to a single example. The first 6 are again training data, and the next 6 are the test data, right? And as if lambda is effectively infinity, right, then we just predict the average, like 0.67, because 2/3 of the examples have y equals 1, and we get that, right? So we get a constant prediction across all examples if the model effectively only learns the bias term, right? And then if lambda is really small, as you can see here, we're trying to fit the data. We're trying to make predictions that are as close to 1 or 0 as possible, right? And then we can make some pretty big errors on the test set eventually. And the goal then is to find a lambda where the average prediction is the squared error between this prediction and these labels are as small as possible. That's the basic idea. Okay, and I should also mention that the choice of lambda depends on your training size, right? So, for example, here the best value of lambda is about 10 to the 1. Still about 10 to the 1. Actually, okay, I made this example very poorly. The object value of lambda is about the same, but they should be different. I apologize for that. Unless I just put it in the for loop. Printed these out. But you can also look at the curves. Right? So here, for 25 training examples, this is test loss, right? If lambda is really small, you overfit to the training data very poorly, very badly. And as the number of training data points increase, you don't overfit the training data as well, right? And so here, for example, actually, the optimal lambda is actually it's the smallest one. And these are fairly representative, right? Okay, just to recap on ridge regression. So ridge regression is just another name for L2 regularized least squares regression. This is the learning objective. Sometimes people put a lambda over 2, divide the lambda by 2, because when you take the gradient of this line, you multiply a factor 2 comes out, and so it makes things more convenient, but that's just details. Large lambda leads to more stable predictions, right? Because in the extreme case where lambda is effectively infinity, you just learn the bias term, so every instance has the exact same prediction. When you have larger lambda, you're less likely to overfit the training data, or you overfit less. If the lambda is too large, your error starts going back up again. And of course, this works with other loss functions as well. Right? It doesn't have to be squared loss. You can do hinge loss, log loss, the whole thing works. Right? In terms of the optimization problem being well posed. Okay, and aside on gradient descent, so when we talked about, or stochastic gradient descent, excuse me, when we talked about stochastic gradient descent before, right, we talked about things being additively decomposable, right? That was one of the key ideas behind gradient descent. And in fact, this loss function is also additively decomposable, right? It's the original loss function plus something, right? And so there are many ways to do this additive decomposition. I've written one, right, where I gave a fraction of 1 over n of the regularization term to every training example, right? And so I'm just going to call this loss function L tilde, and now we can write the original loss function with the regularization term as the expectation over L tilde. There are other ways that you can do the additive decomposition. This is just one way. It's the way that uniformly divides up the regularization term into every with every training example, and you get something that looks like this, right? And then when you do stochastic gradient descent, you just do SGD on this L tilde, right? Where you do a gradient with respect to one training example, and the gradient with respect to the regularization term divided by the number of training examples. Okay, so I talked a lot about how this is a model class, right? But, this isn't actually a model class as written, right? It's just an optimization problem, right? When we talk about model classes, like the class of linear models or the class of neural nets, right? That is a model class as we understand it in this class so far. This isn't quite a model class, right? So is there a connection? And so I'm going to introduce a new concept called norm-constrained model classes, right? So here again, we have the linear model class, right? But I'm going to constrain their norms, right? I'm only going to consider the set of model classes linear models whose norm, and here I'm going to use L2 norm or squared L2 norm, whose norm is less than or equal to some constant c, right? And so here in the two-dimensional case, for c equals 1, the set of norm-constrained models for c equals 1 is a set of all w, two-dimensional w, that sit inside this red circle. For c equals 2, the set of all norm-constrained models with norm less than or equal to 2 sits inside this green circle, right? And for c equals 3, it's all the models, and here again, just visualize the two-dimensional models, that sit inside this blue circle, right? And so clearly, C1 is a subset of C2, is a subset of C equals 3, right? So C equals 1 is a subset of C equals 2, is a subset of C equals 3. And so whatever model that you can learn in C equals 1, you can also learn in C equals 2. So by definition, C equals 2 is a more complex model class than C equals 1. right? Just like how when we talked about the bias variance trade-off, you know, all linear functions can be represented as a quadratic, and all quadratic functions can be represented as a cubic. Here, you know, all norm-constrained linear models with norm at most 1 is a subset of those with norm at most 2. So by definition, you know, we have a hierarchy of complexity in the model classes, even for linear models, even for just linear models, right? And there seems to correspond to this lambda, right? We talked a lot about how as this lambda increases, the W we tend to learn tends to be smaller in the norm, in the 2 norm, right? And when lambda is effectively infinity, then, you know, so in the case of W lambda equals infinity, you can see that it corresponds to C equals 0, right? So there seems to be this, you know, this correspondence, right? And in fact, if you plot the solution to this guy with increasing lambda, you know, and then you plot the L2 norm, right? You see that L2 norm decreases, the lambda increases. Basically 1 to 1, right? So there seems to be a connection. Can anyone tell me what the connection is? Yes?
I mean, the augmented objective is essentially just the Lagrange constraint optimization.
Correct. So hopefully all of you have seen Lagrange multipliers. And in fact, the relationship is exactly given to us by the Lagrangian. Right? Okay, so here I'm just going to look at one training example, and I'm omitting the bias term for simplicity, right? So, you know, if we're here, so I should explain. This heat map is the loss function. So right here, we have the lowest loss of this guy. And then out here, it's higher, right? So if our W is right here, right, the gradient points in this direction, right, in the direction of this yellow arrow. If our current W that we're training is right here, the gradient will point in this direction, right? And so on and so forth. And then, you know, the gradient gets smaller as you get closer to the minimum of this energy function, or this loss function, right? But suppose we constrain the model class to have norm less than or equal to C, for some C, right? And that basically corresponds to all the W that exists within this red circle, right? So if we're here, right? If we're here, then the gradient points, you know, we're minimizing loss, so the gradient points in this direction, right? If we're here, we're actually at the boundary of the model class, right? We're at the boundary of the model class. We cannot actually step beyond the boundary, and so the norm, you know, points in this direction. But if we do a gradient update, we can't actually go in this direction. We have to go along the boundary, right? So if we would actually do a projection step, right? So typically when people, one way to do this in practice, if you were to do this using gradient descent, is you compute the gradient update, right? And then you project the update back onto what is within the norm, right? And so this would be your effective gradient step in this direction, right? And you compute the gradient at that point, and it points in this direction, right? And in fact, if we hit what is going to turn out to be the optimal for this problem, the optimal solution to this learning problem, the gradient at this point is actually exactly parallel or anti-parallel with the loss, right? Right? So this is the tangent normal of the boundary. So this red line is the tangent normal of the boundary of this norm constraint. And the gradient is pointing in the exact same direction as the tangent normal, which means when we project this gradient update back onto the boundary, we get an update of 0. We don't update anything. And in fact, this is the optimal solution. Okay. So the optimality condition is that the gradients are aligned. The gradient of the loss is aligned with the tangent normal of the constraint boundary. Right, and you know, one can write that out as in the standard conditions that people use for Lagrange multipliers. You know, there exists some lambda, right? When they're aligned, that means they're pointing in the same direction. They may not be the same magnitude, right? So there exists some constant factor lambda greater than or equal to 0 such that the gradient of the loss is equal to that lambda times the tangent normal of the constraint boundary. Yes?
So assuming you have like KKT conditions, is this condition, so it's minimizing the Lagrangian via gradient descent equivalent to performing a constraint optimization.
Performing what optimization? Sorry.
Constraint optimization.
Yes, yes it is. Yeah. So right. So these that is right. So minimizing the Lagrangians is the equivalent to performing constraint optimization. There is a correspondence there. Yes.
What if your minimum is like the loss function already?
I'm sorry, I didn't catch
If
it.
the loss function minimum is already contained within your constraint boundary, then the gradient of that be zero, but not necessarily at that point.
That's right. So typically, so right. There's two cases here. One case is typically rare, which is if you have if the global minimum of this loss function is contained inside the boundary, right? Then this condition no longer applies, right? And in fact, you would actually in that case set lambda to 0. Right? That is equivalent to setting lambda to 0, right? Because you're not actually at the boundary. That tends to be the rare case. Right? Typically, you're going to be pushing up against the constraints of the model class. And in practice, that case basically is almost never happens.
So
Yes?
when you take the derivative with W transpose W, that should point greatly outward from the circle that you define. Right? And isn't the gradient of L defined as moving away?
Right, so the gradient, because we're doing gradient descent, these arrows are in the negative, I should clarify. These yellow arrows are in the negative direction of the gradient of the loss, because we're doing gradient descent. That's why it's negative. Right. Yes?
What if there's a local minimum inside your circle? Like, would it depend on where you started?
So if the function was not convex, and there are multiple local minima, then it would depend on your starting conditions, yes. And this would be something you'll encounter time and again when you train artificial deep neural nets, yes. Yes?
So usually you're emitting D, are you basically setting it to 0 in this case?
Yeah, I'm just forcing to be 0 in this case. Like, allowing B to vary as a free variable doesn't change what's going on. It just makes things more complicated. Because if you allow B to vary, then you can like shift this circle around, and it doesn't quite make sense in this very simple example. It makes more sense in the high dimensional. Yeah, it just makes things more complicated without changing the story of what's going on.
But if you allow B to vary, then it won't necessarily fall outside of the minimum, right?
If you allow B to vary, let me think. Right, this loss function is a function of y transpose x minus b. And so if you have multiple data points, then it just changes the shape of the loss function. Okay, so this is our normal constraint model class training, right? This is sort of the type of learning problem that is consistent with our concept of a model class, right? We want to minimize loss function within our class of models, and this is our class of models, right? Linear models with a norm constraint, right? This is our conditional optimality. These conditions will satisfy optimality. This is the Lagrangian. So for those of you who, well, everyone hopefully should recall this from multivariable calculus. This is the Lagrangian, right? So we have lambda here now as one of the variables to optimize, and we just we take this constraint and we put it into the learning objective, into the minimization objective. That's what the Lagrangian does, right? And the claim is that solving the Lagrangian solves the normal constraint learning problem, right? And so the optimality implication of the Lagrangian is that you take the gradient with Lagrangian with respect to, let's say, W instead of 0, then if you do the math, you get this condition, right? This is the gradient of the loss. This is the gradient of the of this term, right? And so if you do this, then you get that it exactly corresponds to this guy, and there's a negative missing here, but otherwise it exactly corresponds to this guy. So this satisfies the first condition. If you take the gradient of the Lagrangian with respect to lambda, right, then when since lambda is also required, it is also must be non-negative. So if the normal of W is less than C, the lambda has to be 0. Is forced to be 0. If the normal of W is greater than equal to C, then then you take the gradient of this term with respect to lambda, then you get this as the gradient of lambda. And then this basically satisfies this condition, right? And so this satisfies the second condition. This is just the standard argument for Lagrange multipliers. Right? And so we spent the first portion of lecture talking about this training objective. This is more consistent with our view of what a model class is, right? And basically, you can show that there is a tight correspondence between these two learning objectives through the Lagrangian, right? For every lambda, let me see if I can get the statement right. For every lambda, you can find a C such that you get the same solution. And so, so for every fixed lambda, it's equivalent to solving it for some C. The reason why people do this, solve this problem instead of this problem, even though conceptually, right, this problem is somehow conceptually more consistent, is that this problem is way easier to solve, way more convenient to solve. Yes?
Why is it easier to solve? Because when you apply stochastic gradient?
Yes, because you can solve this using the gradient, using gradient-based methods. Here, if you hit a boundary, you have to do some projection. Reasoning about the boundary is always more complicated. Yeah. There's no boundary here. Right? Yeah.
Isn't there also an analytical solution for this problem? I mean, L2 regularized training.
Oh yeah, this guy is analytical. This guy is a closed form solution. Let's see. Right. So that question was in homework 1. So the reason why you may use the gradient-based methods is because W might be very huge, right? And the analytical solution requires inverting a matrix that is equal to the dimension of the features by dimension of the features. So that sometimes you don't want to do that. Mm-hmm. Yeah. Because in fact, sometimes SGD is faster than converting that matrix.
Okay.
Yeah. Because inverting that matrix naively is cubic in the dimensionality of the feature dimension. Right? Mm-hmm. And then and the memory requirements is quadratic in the dimensionality of the feature dimension. Mm-hmm. So if the feature dimension was 1,000,000. Okay. And also, it's just here I'm talking about a general algorithm that applies for, as you will see, different norms and different loss functions. Mm-hmm. In the special case where there's two norm with squared loss, then yes, there's an analytical solution.
Okay.
Yeah. Yes.
The point you're making here is that the Lagrangian is easier to solve than the normal constraint. Is that what you're going to say? Or
Yeah. So people typically solve this guy.
L2.
Yeah. Yeah.
But they don't solve the problem.
So the Lagrangian holds C fixed, right? And you could show that, for every lambda, there exists some C, that these two have the same solution.
So which one is that?
This one is what people use because it's more convenient to optimize. There's no right. Okay. So just to recap, so ridge regression is L2 regularized least squares regression. It's equivalent to solving over some norm constrained model class, right? Larger lambda leads to more stable predictions, right? Because you're learning over a smaller model class. If lambda is too large, your test error or validation error starts going up again, typically, because you're underfitting the data, right? And again, this works with other loss functions as well. Okay, so just as an aside, here's a different take on regularization. So this is the ridge regression learning objective, right? And so I'm just writing out here the gradient of this learning objective, which is like the W, and it looks like this, right? So, if we look at this learning objective and this gradient specifically, right? Is there a way to make this part here look like it belongs in this functional form, right? Can we take this guy and make it look like something that looks like this guy, right? And here's the idea we can use to do that. Suppose we hallucinated capital D training examples, where capital D is the dimensionality of the feature space, right? And each hallucinated training example, it activates exactly along one feature dimension, along one axis of the feature space. So E sub D is the unit basis vector that's a 1 in the little d dimension and 0 everywhere else. I'm going to give a magnitude of square root of lambda, right? And the training label, the target, the regression target in this case, is 0. Right? I'm going to give capital D such examples, right? Then, we can write out our learning objective as, wanting to find a W that can fit these data points as well as our original training data points. So we just hallucinate the capital D training examples, right? And so this is what the loss, squared loss looks like for those. And you can show through standard multivariable calculus that the gradient, right, is identical to the gradient for regularization, always. So a different interpretation of L2 regularization is that we just, in the absence of other data points, we just pretended that there were these data points and they pulled us toward the origin. This is an alternative interpretation of regularization, and in fact, they're equivalent. They lead you to the same learning objective. So hallucinating training examples has a very close relationship to regularization, and which we'll explore more of later on in this course, actually. In the case of squared loss, they lead to the exact mathematically equivalent learning objective or solution. The learning objective is different, but the learning objective is the same. Even the learning objective is the same. The gradient certainly is the same. And we'll talk about this more later on in the course, when we look at other forms of regularization. Okay, we can also extend this to multitask learning. So multitask is the goal, is where we're trying to learn over two in this case, supervised prediction tests at the same time. For example, we have a training set of what Alice considers Stan, and a training set for what Bob considers Stan, and we have limited training data for both. But we have a hypothesis that Alice is similar to Bob. So the weight vector we learned for Alice should be similar to the weight vector we learned for Bob. Right? And so we have two training sets, each are relatively small for task 1, which I denote by superscript 1, and task 2, which I denote by superscript 2. Right? So option 1 is we're just going to train each separately. Right? We solve for the model for Alice, which I denote W, we solve the model for Bob, which I denote by V. Right? Now both models have pretty high error because the training set is pretty small. Right? So can we do better? Right? Well, okay, well we can say let's write out a joint learning objective and just like write over both the training problems and then let's solve it. Actually, this particular formulation doesn't do anything because V's and W's never interact with each other in these learning objectives. So it's equivalent to solving this separately and this separately, which is what we were doing before. So this doesn't accomplish anything by itself. Here's one version of multitask regularization that does accomplish something, right? So this is the standard regularization for the model for ridge regression. This is the training loss for the two training sets. But I'm also going to enforce that W and V be close to each other. And I pay a penalty for the distance between W and V, right? So this prefers W and V to be close to each other with this gamma term controlling the trade-off. This is called multitask regularization, where the two tasks are regularized to be similar to each other, right? And so you can actually plot the test loss, in this case I'll plot the task loss of task 2 as a function of gamma. So the two tasks are similar in this example. So as gamma increases, the test loss decreases, right? But the two tasks are not identical. So if gamma is too large, then actually the test loss increases again. There are, of course, other ways to do multitask regularization, and regularization can become very complicated as you look at more complicated supervised learning tasks. This is just to give you a flavor of what a more complicated instance of this might look like. This is not on the homework. Okay, so for the remainder of this lecture, we're going to talk about Lasso, which is used to refer to L1 regularized least squares regression. So L1, right, is, as you might remember from the beginning of the lecture, is the sum of the absolute values of the entries of W. L2, or squared L2, is the sum of squares, right? So, so this is the blue line here is the L2 regularization penalty, right, and the red line here is the L1, right? So the loss increases linearly as this component of W increases in magnitude, either positive or negative. And if they're both 0 or they're minimized at the origin, right? For L2, it increases quadratically, right? And so if we look at this penalty, right, for L2, right, the difference between a component of W being root 2 versus 1 is the same as the difference. If I increase W, or in this case it's a one-dimensional W, but if I increase any component of W from 1 to root 2, the increase in penalty is the same as if I increase W from 0 to 1, right? Because the L2 penalty is quadratic. The L1 penalty is linear, right? So if I increase W from 0 to 1, the increase in penalty is the same as I increase W from 1 to 2, as opposed to 1 to root 2. One thing that I want to just quickly mention is that this function is not differentiable everywhere. In particular, at the origin, it is, it's not differentiable. And so what people do is they use the notion of what's called subgradient descent, which uses a subgradient to solve the optimization problem. And a subgradient is of a function R around a point A is simply defined as follows, right? So it's all this, the actual interpretation the actual interpretation of this is that it's all the slopes. So it's all the slopes that lie beneath this point. That's the actual visual interpretation of what's going on. So when a function is differentiable at that point, then this set is a singleton set and it's equal to the actual derivative, right? For L1, right, this is what the subgradient looks like. It's -1 if the component of W is less than 0, it's +1 if it's greater than 0, and when W is exactly 0, it's all possible slopes between -1 and +1. Right, so there's an infinite number of subgradients at the origin. And of course, this generalizes to the multivariable case. You just apply this definition for every dimension of W independently. Right? So, for L2 regularized z squares, this is the gradient of the regularization part. For L1 regularized z squares, this is the gradient for the regularization part, or subgradient. Okay, so let's do the same exercise with Lagrange multipliers. Right, so now the constraint is we're constraining the 1 norm by less than or equal to c, rather than the square 2 norm by less than or equal to c. Otherwise, everything's the same, right? And so we have the same thing as before. These are the unknown. These are the negative gradients of the unknown of these points in the unknown in this case. This is the boundary of for L2. This is the boundary for L1. So purple is the boundary for L1. So you don't get a circle, you get a tetrahedron, right? So everything inside this purple square are W, whose 1 norm is less than or equal to c. Right? So let's say we're at the boundary, right, of this model class, and we compute the gradient. And we take a step in the negative direction, we project it back onto the boundary, right, and that's here, right? And then we're going to follow, and of course, let's just follow this logic until we get to this corner, right? And now we compute the gradient, right, and it goes in this direction. And at this corner, there's a continuous range of possible tangent normals to the boundary at this corner, right? There's a continuous range, as defined by this, right? And one of those tangent normals at the corner is aligned with the gradient, of the loss, and therefore we're at optimality. Right? As long as there exists a subgradient that is aligned with the tangent normal, right? That is aligned with the gradient of the loss or the negative gradient of the loss, then that's sufficient conditions for showing that we're at optimality. And what this implies is that many of the solutions of this optimization problem will be at the corners, right? Will be at the corners of this of the boundary of this model class, which means many of the components of W will be 0, right? So you get a W that will have many zeros in its solution. Right, solutions tend to be at corners. So this leads to a concept known as sparsity, right? A vector W is sparse if it's mostly zeros, or has many zeros, right? If we wanted to be like, if we want to write down this, we wanted to formalize this more precisely, we would say that it has low L0 norm, right? A vector is sparse if it has a low L0 norm. So wouldn't we do L0 regularization? Why don't we do L1? Why would we not do L0? Any guesses? Yes? Exactly. L0 is actually not continuous. It's flat or discontinuous everywhere, right? Just like how 0,1 loss is flat or discontinuous everywhere. In fact, L0 is not an actual norm. L1 reduces sparsity, right? Because the solutions tend to be at corners, and it's continuous, right? And it's convex. Why might sparsity be important, right? One reason is a computational or memory argument, right? So, you know, for example, if X corresponded to text, right? And we wanted to store X as a vector, most texts, bodies of text do not contain most words in the English language, right? So you get a very sparse vector, right? And so you might want to, you know, store this thing more efficiently, right? So if you could either store a million numbers, most of them are zeros, or you can just store index value pairs for the non-zeros, right? And if the W you're learning is also sparse, then, you know, you might want to exploit the fact that you expect W to be sparse. Okay. The dot product is also more efficient, right? Sometimes the true W is in fact sparse, and we actually want to recover the non-zero dimensions of W, perhaps for some downstream data science or interpretation tasks. Right. And so, you know, people have studied Lasso for a very long time. I've written a lot of papers about Lasso. And so, you know, suppose the data, right, suppose the data that generated the training data, right, was generated according to a normal distribution, right, with some true model parameter W star, where W star is sparse. So the true model that generated the data is in fact sparse. Then under some conditions for lambda, right, now this is just one result. I just want to give you a flavor of how people sort of analyze a lasso. This again is not in the assignments. But then if, you know, with high probability increases with failure probability that decreases vanishing quickly with the number of training examples n, right? Then the W that we learned through Lasso, right? One regularized least squares regression, that the non-zero entries of W is guaranteed to be within the support of the true W star, which means that the parameter recovery, which parameters of W are actually non-zero, we get high precision, right? And then other conditions, we exactly recover the support, which means we also get high recall. And so this is one type of guarantee that people tend to try to prove when analyzing Lasso. Now, if you believe that the data, the model that you want to recover actually is sparse, you know, what are conditions under which one can sort of recover it? Okay. So here I'm showing the parameter weights of the two dimensions. So remember, dimension 1 is age greater than 10, and dimension 2 is whether or not the person is male. And so these are just different solutions as you vary lambda for L1 versus L2 regularized least squares progression, right? And so this is, so every one of these points is a solution, right? So this is, you know, the W corresponding to this feature equals to 0.3, the W corresponding to this feature equals 0.03 or something like that, right? And so indeed, you see that, it's a little hard to see in this example, but you can see that W, for L1, you zero out one of the feature weights, you know, for sufficiently high lambda. Right? And as lambda increases, the norms get smaller. As lambda decreases, the norms get bigger. Right? So for some lambda, for the existing lambda, after which you could beyond that lambda, the weight for the second feature is exactly 0, whereas for L2 regularized regression, for ridge regression, the weights get smaller and smaller and smaller and smaller, but only become 0 at infinity, where the regularization is infinity. Let's talk a little bit about optimizing Lasso, right? So we see that Lasso gives us a sparse model, right? Will stochastic gradient descent find it, or stochastic subgradient descent? Will it find this sparse solution? The answer, unfortunately, is no, right? It's actually hard to hit exactly 0 using gradient descent. you'll overshoot 0, and then you'll shoot back and shoot back. So you'll get a W that is converging towards a sparse solution, will never actually be sparse if you use gradient descent or subgradient descent. Right? And if you actually care about finding a sparse solution, then this is a problem. Right? And so there are other methods. These methods are beyond the scope of this course. Typically these days they're just part of some optimization library you call, like in scikit-learn. Well, one solution is called iterative soft-thresholding. And the basic intuition in which they formalize is that if you do a gradient update and it causes the weight vector to pass 0, you clamp it at 0. Yeah.
Is there a version of that that works for negative parameter values?
What do you mean by negative parameter values?
Like if the optimal, because if the gradient update passes 0 value.
Yeah, it could pass 0 in any direction, negative, positive, positive, negative.
Oh, okay, I see.
Yeah. I mean, it's more complicated than this intuition, but that's a high-level intuition.
Okay.
Right? And so this is a modification to gradient descent or subgradient descent that says, I know that the solution is supposed to be sparse. I know that, in fact, there are multiple gradients at the origin, right? Because there are multiple subgradients at the origin, and I just computed one. So as I pass through the origin, maybe a different subgradient is valid. And so that leads to the intuition. That's mathematical justification. It leads to this intuition that if we pass through the gradient, we just clamp it at 0. Unless it's able to pass through the gradient at a really high rate. It would have to pass the gradient by a lot, right? Yeah. That's what soft thresholding actually means. Right? There's a threshold under which if we don't pass the gradient pass through 0 by that amount, if the gradient update doesn't pass us through 0 by that threshold, we clamp it at 0. Yeah. So that's the intuition. It's called ISTA, iterative soft-thresholding. A lot of people have written a lot of stuff about it. So if you're interested in learning more, there's one resource at the bottom here that's linked to. Okay, so just the recap of Lasso versus Ridge, right? So whether or not you choose to use Lasso versus Ridge, L1 versus L2 regularization, depends in part on your modeling assumptions. Do you want to learn a sparse model? Do you believe that the true model that you want to recover is actually sparse, right? Predictive accuracy. So Lasso, it turns out, actually it will lead you to a model that's not as accurate many times, right? And so what people often do is use Lasso to identify the features that matter, right? And then they rerun that learning process using only those features, and then they turn off regularization. Or you use a very small amount of ridge regression regularization. So people often do this when they use Lasso if they want to get the highest prediction accuracy as possible. Right? Ease of inspection, right? If your model is sparse, right? It has, if it has like 1,000, if you have 1,000 feature dimensions in your model, and only 10 of the entries are non-zero, you can just look at them and see what your model is doing, right? You can actually visually inspect them. So in this sense, people often refer to Lasso or sparse regularization as giving you a quote-unquote interpretable model. If you use tricks like ISTAs, like soft thresholding, that are more advanced in stochastic and gradient descent, it often turns out to be the case that Lasso, you have to use these extra tricks in order to optimize for Lasso if you care about recovering sparsity. Any questions? Yes.
So how can you know before the training that the W that you're trying to learn is sparse enough?
You don't know for sure. So it's an assumption you make. Yeah. Like you don't know for sure if your model if a linear model will do well or not. Right? The choice of using a linear model class is based on the assumption that it's reasonable. So at the end of the day, when people study the theory of these things, they say under the assumption that this is reasonable, then would you expect it to work well? Like how much training data, what values of lambda, you know, for what level of sparsity, so on and so forth. But at the end of the day, you don't know for sure. Yeah. You can only use this type of analysis and theory and thought process to help guide you, right? So like if you use Lasso and it turns out your model still isn't sparse, right? Even after you turn on Lasso regularization, then maybe the true model isn't sparse, right? But those are the types of thought processes people go through when they use these tools. Okay, so just to recap regularization, we have ridge regression, Lasso, multitask. You know, as you become more familiar with machine learning and start working on increasingly more complicated learning tasks, you'll probably come up with your own crazy combination of regularization techniques, right? And so that is the hope. And so just to recap the pipeline that we've talked about for the first few lectures, we have training data, we choose a model class, let's say linear, we choose a loss function, let's say squared loss, we have a regularization term that helps us control for overfitting, we do cross-validation to see which regularization strength gives us a model with the lowest validation error, and that allows us to do model selection because regularization corresponds to different choices of model classes constrained by the norm of the weight vector in your linear model class. And this is what you need for the Kaggle competition for mini project 1. For the next few lectures, we'll be talking about nonlinear model classes like decision trees and ensemble methods like bagging and random forests and boosting, and no recitation this week. That's it.